I'm very excited to share with you today some of the work that my group does in the area of organic printed bioelectronics. So let me see if I can actually control the slides. There we are. So this is my team at KAUST. The lab is called Organic Bioelectronics. So we all deal with organic electronic materials. These are carbon-based semiconductors, which have very interesting transport and mechanical properties. And that's why we use them at the interface with living systems. We look at, in our lab, a lot of fundamental mixed ionic and electronic charge transport properties of these organic electronic polymer films. And once we find interesting candidates, we go ahead and make micron scale and sometimes larger, as I will show you today in the printed devices, large scale sensors for detection of, for instance, activity of neurons, integrity of lipid bilayers or cells or their functionality, as well as devices that can detect certain biomarkers from bodily fluids. And everything is done, all these devices are using these organic electronic materials, these conducting plastics for diagnostics applications. Now, when we want to make these devices, typically the way how we go is through photolithography. And maybe some of you are familiar with this technique. You need a clean room, a quite expensive bulky instrumentation, and multiple steps of processing. You start with lifting of your metal, putting some layers of photoresist and insulators, and use of lots of solvents and such. And eventually you come to a point where you have a device. And here I'm showing you such a device. This is an organic transistor. There's a source and drain gold electrode, and in between an organic electronic material. And as you can see here from the scale bar, this is a device that is about, 50 to 25 micrometer size. So very precise devices you can make with photolithography. And we're very happy to be able to do that here at KAUST for certain applications. But as you see, this is like a long procedure that is required to make such a device. Therefore, and this is how they look like once we prepare them. Here, there are like 6 identical channels, transistor channels, and 2 what we call lateral electrodes fabricated next to it. As nice as photolithographically produced devices looks like, it also takes quite some time to prepare them. Therefore, printing technologies come as an alternative to fabricate these devices, and especially when you want to fabricate these devices on unconventional surfaces, for instance, a field that we know as flexible electronics. And as you can see, the market forecast for these printed and flexible only for sensor technologies is increasing dramatically since 2014, and will continue going more in the coming years. Now, the biggest advantage of using, I think, printing as an alternative for fabrication is that, as I said, you can use very different substrates. In the previous slide, you saw that everything is happening here on fused silica. So this is like glass substrate or anything rigid and resistive to solvents as well as temperatures. You don't have that requirement when you want to print materials and fabricate these devices on, for instance, polymeric substrates that are bendable, flexible, or elastic. The geometry is customizable. You can generate various devices with different sizes. It's the technique that is adaptable for large scale. In photolithography, you may be using just one wafer, but when you're doing printing, you can print very large areas and therefore generate lots of devices at quite a short time. And this, of course, reduces the production cost. It also comes with a minimal waste of materials or solutions that you use, because you only print the amount of material that you need. You're not relying on any masks. The fabrication is rapid. You typically don't need high temperatures or there's no vacuum deposition, which takes quite some time. And therefore, the technique is quite environmentally friendly. And resolution these days can go down till 40 micrometers. So that looks quite a nice way to do it. And in our lab, we use inkjet printing. So this is one type of printing process to generate organic sensors. And if I go through just very quickly how this is happening, so the inkjet process is a drop-on-demand technology. As the name suggests, you want to have a drop of the solution on the substrate, and that's what you do. And for that, what you need is a cartridge that contains the ink. And there's a nozzle here that is just a tiny hole that is capped with a vibration plate and a piezo element. So piezo elements, what do they do? As soon as you apply a voltage, this causes a change in the shape of the piezo element that changes the pressure of this cartridge and makes that ink basically to drop from the nozzle opening. And this pressure relief is obviously generating this drop, and that drop goes to the substrate, and there you go, you have a printed surface with the material that you're working with, and that is the ink. Obviously, there are lots of things that affect the printability of material, so you cannot print everything. That ink needs to be optimized such that it has optimal rheological parameters. For instance, its viscosity is very important. Think about something very liquidy will be immediately moving from this nozzle. When you have something like honey that's very slow to move, obviously printing that will be much harder. So we spend a lot of time to optimize the ink properties so that we have electronic materials or insulators or anything that is used in semiconductor device fabrication technology. So we need to first prepare the ink. And then there are, of course, parameters that are related to the inkjet printer itself, such as the characteristics of this print head, like the diameter of the nozzle, how many times, how often you eject this, the drop from the nozzle, the voltage that you're applying, the channel, the pressure in the chamber. All of these are also further parameters that one needs to optimize to have a nicely printed surface. Now, in the lab, as I told you, we are using inkjet printing as the technology. We have a Dymatics printer that's about these dimensions, 6 to 67 centimeters. That means it's quite actually small, so you can put it anywhere you like. And that is working with a certain cartridges. This is the part of the inkjet printer that contains the ink. And the one that we are using has about 16 nozzles with a diameter of 21 micrometers, where the fluid is basically dropping. And today, all I'm going to talk about are some applications of the inkjet printed devices that we fabricated in the lab. And these devices are using mostly PEDOT PSS as the organic electronic material. This is a conducting polymer that is commercially available. There's a company that even sells this material in an inkjet printable format. So you don't need to even do much optimization yourself. So the only thing you need is an inkjet printer, the nozzles, and the conducting polymer, and then you can go ahead and start preparing flexible bioelectronic devices. And one thing that I forgot to say, in terms of environmental friendliness, a material like conducting polymer is a water dispersed polymer, so that makes all the hazards that can come from, for instance, chlorinated solvents much less. So this is the first part of my talk. I will show you applications of printed PEDOT PSS devices, and then in the end I will also show you how we used a 2D material this time that is called MXene in a printed flexible biosensor configuration. So let's get started with printed electrophysiology electrodes that are used for gel-free epidermal sensing. And I'm going to explain all these terms to you if there are some of them that you're not familiar with. So as you know by now, there are several devices that you can find in the market that detect signals from the surface of the body. Now, these devices are called cutaneous devices. Cutaneous means on skin. Now, what do these devices do? They detect either the activity of electrically active cells from our body. For instance, the cells that you have in your brain, these are called neurons. They fire, they cause certain ion fluctuations, and when they do it all together, the whole network, they generate certain waves, which you can then detect if you place an electrode on the surface of the brain. So these are called electroencephalogram, EEG measurements. Similarly, heart activity, heart has also the cardiac cells that are electrically active, and when they fire together, that causes beating of the heart. You can actually detect this activity using, again, electrodes that are placed on the surface around the skin that is close to the heart. So these measurements are going to be called ECG. Similarly, for muscle activity, muscles are also formed of electrically active cells. You can measure them if you use electrodes close to where this activity is originating at. So all such applications, and similarly, maybe certain biomarkers you can detect from the sweat. You can make devices that are specific for those biomarkers and reach those signals from the surface of the skin. So these are called cutaneous devices. Now, in this first part, I'm going to show you how we do electrophysiology studies using printed PEDOT PSS electrodes. Now, why do we do this? Are there no electrodes that can detect electrical activity from the skin? Yes, there are. And in fact, if you have ever been in a doctor's office who wants to detect some of these signals from you, for instance, EMG or ECG or EEG, you may have seen such electrodes. So these are called gelled AgAgCl electrodes. So AgAgCl is just a non-polarizable electrode, which is covered with a gel that contains ionic charges in it, so that the rigid AgAgCl electrode and the dry AgAgCl electrode has a very nice interface with your soft skin. And typically, these electrodes give quite good quality of signals. That's why they're the standard electrodes. However, because of this gel that the electrode is connected to, for some people, this gel can cause some irritation. And because these electrodes are rigid, there are also some motion artifacts. So if the clinician wants to take long-term signals, that becomes hard by using such gelled AgAgCl electrodes. Another problem is that the gel dries out over time. And when the gel dries out over time, the signal quality goes down. And it's quite lengthy also to set up multiple electrodes, for instance, if you want to take signals from all around the head. That is quite problematic. And as you see, these are quite large electrodes. Large electrode means you have low spatial resolution. So you cannot reach the activity of a few neurons, let's say, from the skin if you use such a large electrode. So you need to get to the level of the cells to be able to communicate them properly and with a good spatial resolution. Now, for that, there are some desired properties that are targeting these challenges. For instance, we want to use dry electrodes and get rid of gels to get rid of any of these problems, so that you can have, and these dry electrodes need to give stable and long-term recordings. They should have low impedance, and that's something hard to achieve for many materials, because again, once they are dry, they make not very good interfacing with the skin. They need to make good contact, so that means they need to conform on the curvilinear parts of our body, right? Like it's easy to interface something that is rigid with a rigid electrode, but once you have certain shapes, then that means your electrode needs to get into that shape as well. And obviously they should not cause any discomfort, so that they can be used for a long time. And needless to say, anything you put on your body, you want them to be non-toxic. So that calls for new materials, right? And that is where PEDOT PSS will come into play. And I'm going to show you in this example how we use PEDOT PSS for EMG recordings. just to wrap up again, what was EMG? This electromyography. This is the neuromuscular activity of muscles, and typically you would see signals like that. So this is in electrophysiology, this axis is showing you the strength of the muscle activity, and this is the time, how fast that signal appears. So here the neurons that form those muscles are just firing, and the action potentials they are firing at the muscle fiber can be recorded with these EMG electrodes. So here, for instance, the muscle is contracted, and then this part is relaxed, and then it's contracted again. So there are neurons again like firing, and this is when you can see their activity. And typically, the frequency range of interest for EMG is about 10 to 1000 hertz. So any material that you use, you want it to have low impedance at this frequency range. And it should be able to detect EMG spikes that vary between from a few microvolts to few millivolts. So that's actually quite nice and not so hard measurements to be done. Therefore, I think printed electronics can give quite a nice solution for the problems that we talked for EMG specifically. And people have actually done certain printed, dry, and flexible electrodes for EMG. Here you see one example, for instance, that is electrodes that is fabricated on flexible polyimide substrates that are connected with these like long wires. It does quite nice recordings, these sample electrodes compared to the reference AGA-GCL. One, I think, revolutionary idea is to print materials on tattoo paper, and then once you tattoo that paper on your skin, you can basically have an electronic material on the skin that can detect EMG activity, and that's what this paper also shows, quite a nice one. But in all of these applications, so making the material is nice, but the system integration is the problem. Connecting wires to these tattoo electrodes is quite problematic, because you come to a very elegant electronic film on the surface with some either wires or really large inflexible electronic devices, and that causes a lot of issues. Especially they have resistance to motion, and they do degrade over time, so it's not really working properly. Now, the idea that we came up with, we said, how about we make PEDOT PSS-based tattoo electrodes on the skin, but we do also interfacing with, again, the PEDOT PSS, but this time printed on a textile. Because now you can actually, if this is your skin, you can tattoo the PEDOT PSS, the conducting polymer, on the skin surface, and you can contact it by wrapping basically this textile, conducting textile, again, PEDOT PSS based textile. And the whole thing can be connected to the acquisition system. Now let's look at the impedance, the skin impedance of these textile tattoo electronics. And this is how the configuration looks like. You use a 3-electrode system. This is your reference, a counter, and your working electrodes. This is the tattoo wrapped with the textile electrodes, and this is the electrochemical impedance over a large frequency. Now the gelled electrodes, you see, they have quite low impedance. When we go to textile, tattoo-textile electrodes, they do have larger impedance, but at a region where we want to detect signals, this is about like 10 to 1000 hertz, they're actually not too bad. And I'm going to show you how they are not too bad by showing you the actual measurements that we have done. But first, let's look at how these tattooed PEDOT PSS look like on the skin. So this is when the skin is just undeformed, so there's no change. Once we compress it, you see there's no change really in PEDOT integrity, and after compression it goes back to its initial state, and this is all because of the softness of the polymer that we are using that is able to move with the skin's motion. Again, here we are looking at the resistance of this PEDOT PSS tattoo as we put it on the fingertip, and then you're moving the finger with a 30-degree or 90-degree configuration. And as you see, the resistance is not really changing as we are basically deforming or changing the compressing the polymer back and forth. Now, these are the results that we got from a volunteer that carries this tattoo-textile electronics, while the person is basically doing some biceps activity, taking a few weights and then moving them up and down at a given time and with a periodicity. And at the same time, next to these tattoo-textile electronics, we are also recording the same activity, this time using standard AGAGCL electrodes. And this is at time 0 when we start doing the experiment. This is after 3 hours, and this is after 6 hours. And now here I'm showing you just the signal to noise ratios, meaning that how good the quality of the signals we get at 1 hour after we start the measurements, 3 hours after, and 6 hours after. And obviously, the higher the signal to noise ratio, the better the quality of the recordings are. Although with the tattoo-textile electronics, you start about half the quality of the standard AGAGCL electrodes. Over time, the AGAGCL electrode quality is decreasing because we are really losing the gel that is making AGAGCL special, whereas the flexible and dry tattoo-textile electronics is getting better as the skin also produces some sweat. But that sweat is not affecting much the AGAGCL because of the degradation of the gel electrodes. Now, this was the first example that I wanted to show you how you can use printed organic electronic materials for interfacing the surface of the skin. Now, I want to show you another application where we again print PEDOT PSS, but this time on a completely different substrate and a completely different application. And our application is a metabolite sensing, and particularly a glucose sensor. Now, this is a typical glucose sensor, electrochemical glucose sensor that you can find in the pharmacies. And if you open this box, what you will see is a transducer that is typically an electrode or a transistor, and a biorecognition unit. This is the enzyme, the protein that is specific to glucose. So this enzyme is integrated on top of the electrode, and it is going to be used when we want to detect glucose using electrical signals. Now, the reaction that takes place inside of this box, once the glucose in the blood goes through the strip inside and on top of the electrode, is very simple. And it's one of the basic redox reactions that take place all the time in our body. So glucose interacts with the enzyme glucose oxidase, and in this process, glucose oxidase is reduced. It gains an electron, okay? And this electron is then transferred to a mediator. This is think about it as a chemical species that can shuttle electrons. So they take electrons and then they vehicle it. It's like basically a vehicle that takes those electrons, and those electrons are given then to the electrode. And the net result is obviously an electron that the electrode takes for one glucose that is interacting or reacting with glucose oxidase. So this is basically the mechanism how you do electrochemical detection by using an electrochemical system. Okay, so electrodes and enzyme and their reaction in between. Now, the same thing that I'm talking about can be actually fabricated on a disposable paper substrate. And this is literally this PEDOT PSS system that we print on a paper, and you don't need to print it on such a small paper. You can actually do the fabrication on an A4 paper and go from, make multiple electrodes at a very short time. And here I print a reference electrode from PEDOT PSS. I print this counter electrode from PEDOT PSS, and these two you will need when you want to do readouts from this working electrode. And this working electrode is the one that contains the enzyme that I talked about, the glucose oxidase, and the mediator, and a few other species that I will show you that is used either to insulate the contacts from any other liquid so that you only have detection in this area, as well as a layer that we use to acts as a barrier to everything else other than glucose. And this layer is called naphthalene. But just to wrap it up before getting into details, what I want to tell you is you have an A4 paper and an inkjet printer, and literally an enzyme, a PEDOT PSS, naphthalene, and a dielectric ink, and you just print it on this A4 paper, and basically do all the electronics part by using one single material, that is PEDOT PSS, a water-based conducting polymer film. Now, once we do this coating, so obviously this working electrode is the part that is going to do the whole business. So this is a scanning electron microscope image that looks at, at the molecular level, at an atomic level, how these layers look like. So the first one here is PEDOT PSS. That's about like 160 nanometers that we print. This is the substrate. This is PEDOT PSS. This is the biological coating. That is the enzyme and the ferrocene that we print also using the printer. And on top of it is our naphthalene layer. This is the anti-interference layer that we print. So this is the whole business end of the sensor that we would prepare. Again, the top SEM images. So this is the PEDOT PSS layer. This is after we put the biological enzyme, print the biological enzyme on the surface. And this is after we encapsulate it with this naphthalene layer. And this is how a typical device look like. And here I'm showing you some current voltage characteristics that we are going to use when we want to get the readouts against glucose. Here I'm showing you the sensor without the interference layer in a buffer, in water basically, in various types of metabolites as well as glucose. You see, glucose generates a much higher current from the sensor, but the other, species like ascorbic acid, uric acid also generate some sort of signal. So this is why they are interference, and that's why you need to put this naphthalene layer, this anionic membrane on top to suppress all these signals from the interference and let only glucose to pass. And naphthalene does it because this is a negatively charged surface that repels all the negatively charged species that are commonly found in our bodily fluids. For instance, saliva has a lot of ascorbic acid, uric acid, as well as lactate and lactic acid. So you don't want to have these negatively charged species coming close to your sensor and interact with your PEDOT PSS. That's why you're using naphthalene. And this is the portable device that we use to monitor the electron, to get the output signal of the sensor. And this is a real-time measurement. So this is, I'm monitoring now the current of this electrodes as a function of time as I introduce certain concentrations of glucose. As you see, at each addition of glucose, there's an increase in the sensor's current. Because of that reaction, the electrons are formed, and PEDOT PSS just takes those electrons, and that contributes to its current. And this is just what we call a calibration curve. So that's the output of the sensor as a function of glucose concentration. So the more linear this thing looks like, the better you are off with the sensor. And in this case, the highlighted area here is the concentration of glucose that we are interested in saliva. So around this concentration, we can say a person is diabetic or not by looking at, if whether they are above this threshold or below that threshold, and the sensor has quite nice linear response to glucose at this low concentration range. If you introduce random concentration of glucose in saliva, so this is experiments that we do by spiking certain concentration glucose in saliva, you see the sensor is responding to saliva. It's not affected by any of those interference in it. And again, a nice calibration curve that we get. Random concentrations that are decreasing, increasing, decreasing, increasing. Sensor current is changing accordingly. And because of an encapsulation procedure that we apply, the sensor response is also comparable almost about a month after almost a month of storage. So you can make these paper sensors and just keep them in the fridge. After 1 month, you see similar response to a low selected concentration of glucose in saliva. So what I showed you now is a basically paper-based sensor where all the electronics are made of an organic material and everything is printed, including the organic material and the biological unit. So inkjet printing not only prints synthetic materials or electronic or insulating materials, but it can also print biological species and keep their activity, as I show you in these measurements. And PEDOT PSS is a molecule, is a polymer that detects also species other than glucose without having any biorecognition unit like glucose oxidase. For instance, it is sensitive to dopamine. When you add dopamine on top of PEDOT PSS, you see there's some peaks that are appearing here that is coming from the reaction of dopamine with PEDOT PSS. Similarly, for ascorbic acid, it is sensitive. For the other sensors, this was not a good property. That's why we use Nafion layer to remove these, ascorbic acid, uric acid. But in certain applications, if that is, if in the environment there's only ascorbic acid, you can detect this presence just by using PEDOT electrodes. Similarly, for uric acid, we can also do detection without using any other molecules, any other biorecognition units. And as you can see, all these sensitivities kind of happen at different voltages. So for instance, here for dopamine, you are at a lower voltage. For ascorbic acid, the maximum sensitivity is at a different voltage. And for uric acid, that shifts even further to higher potentials. And talking about potentials, as you see, for all these devices to operate, we do need a power supplier. So without a device that applies this potential, and in the previous experiment that I showed you that was like a handheld device, you cannot make this sensor operate because you need to apply the voltage. And just a very short introduction to an integrated sensor that I want to show to you, a self-powered sensor that we made for uric acid or dopamine with a group of Daria Baran, who's going to talk about printed solar cells tomorrow. So what we did with this group is to print organic solar cells on the same substrate where we have these PEDOT PSS-based sensors. And as the organic solar cell is a device that generates a voltage upon application of light, all this device, the sensor, is basically operated by the power of light. And light, where do you have it? Well, you have it everywhere. So that's a good thing that makes the sensor almost working without a power source or an external battery. And the sensor's performance is very similar to what you would get if you actually use the potentiostat, like another type of device that applies the voltage. And you can make these devices again on flexible substrates and then put your own skin and do some measurements from the sweat. For instance, uric acid or dopamine. Dopamine, we don't have much in the sweat, but uric acid we do have. Or many other species that you want to detect. You can change the units of the sensor and integrate it with a solar cell. Now, the past 5 minutes, I want to just talk about the printed sensors, the ones that we make this time by using a completely different material, but showing as good performance as PEDOT PSS. This material is a 2D material, a titanium carbide-based material that is called MXene. Maybe some of you have heard about it. This MXene is existing in water as also as dispersion, so it's not perfectly dissolvable, but we find ways, certain tricks to print it to surfaces. Now, MXene alone cannot be printed from water, because if you try to do that, like its viscosity is not high enough. Therefore, we use certain surfactants. These are molecules that are charged with ions, like anions or cations. And when we do some mixtures and see if we can print better. And as you see here, we are trying a variety of surfactants that have different properties. And here I'm showing you the surface tension. That is about, how well you put that drop on the surface, and the conductivity measure. So MXene alone without the surfactant has quite high conductivity. And as we introduce these surfactants, the conductivity goes down, but we found out that saponin is making the surface tension perfect, and is also giving quite nice conductivity that is in the order of somewhere between 500 and 1,000 Siemens per centime. And you can put the MXene electrodes on these tattoo papers that I just told you about for PEDOT PSS. You can print it, you put it on the skin, add some water. Maybe some of you remember this trick from your childhood. Once you add the water, you remove the paper part, and what you're left is with the tattoo, the electronic material, the MXene on the skin. And we interconnect the MXene, this time using a copper wire. I'll show you another trick how to do that. And MXene is biocompatible, that we show with separate measurements, but it's also not leaving any of these, stains, any skin reaction that some gelled clinical electrodes do. And the way how we again interface MXene is by using this conducting copper tape, but you don't have to use it because this is not very nice. That looks quite ugly. But you can do something else. You can print MXene on a PEDOT substrate. PEDOT as a flexible material, it is also self-standing, and there's a formulation how we can make it self-standing. And now we can put the MXene on one side and basically just wrap the whole PEDOT around the skin. And what do we do with this printed MXene films on flexible PEDOT? Well, we can do a variety of things. We use them as electrophysiology electrodes, as I showed you in the beginning for the PEDOT PSS. You can use it as an ion sensor if you put an ion selective membrane on top. So you can measure, for instance, the activity of the sweat of the skin, therefore the body. But you could also measure certain antibodies, antigens, if you put antibodies on the surface of MXene, because one nice thing about MXene is that it contains functional groups on its surface, which allows you to anchor different biorecognition species. For PEDOT, that's a bit hard to do, but for MXene, it's much easier. And I'm showing you just how we use this to measure hard activity. So these are ECG electrodes when we use MXene in comparison to AGGCL. And as you see, the impedances are quite similar. So we do get similar ECG signals both with MXene and PEDOT PSS. And the devices are quite stable. My video is not working. Oh, no, it's working. All right, so here you see I'm measuring ECG. So these are ECG signals in real time. As soon as you remove it, you lose the signal, you put it back, you get the signal again, and you can do it back and forth constantly. Nothing is happening to MXene. It's quite stable and conformable with the skin. You see how nicely it is interacting with it. All right, so that was for the electrophysiology. For the sodium sensor, it's again very easy. We just put an ion selective membrane on top of the sensor and detect basically the sodium concentrations from the sweat. Something similar you can do by tethering antibodies on the surface, and then with that specific antibody, you can measure cytokine and an inflammation biomarker in the sweat with quite nice sensitivity. Now, I think this is the last slide that will allow me to finish. Printing technologies are amazing, but I think the trick is really on the library of materials that we use. For instance, we have very different polymers with very different properties that we can use in devices that we generate with photolithography. But these materials should be inkjet printable so that we can make much better sensors, or sensors, as I showed you in this talk, that have different properties by leveraging the properties of different materials. So we do lack we have a lack of materials that can be inkjet printable, and I think this is mostly on the side of organic electronic materials. Now, to conclude, I showed you that printing offers a cheap, fast, and easy alternative to the fabrication of biosensors. I showed you that the self-powered and energy-efficient, sustainable printed biosensors, they're essential for the flexible revolution that we will have. I showed you that it's very important and it's very urgent to extend the library of materials so that we can achieve multimodal sensing, power conversion, and maybe even stimulation. And also we need to extend the application areas to power conversion devices, and integrated systems is really the key. With that, I would like to thank my whole group who are involved in this work. Particularly, I showed you the work of Abdullah, the PhD student who just heard from, as well as our alumni, Eloise BR, who did most of the PEDOT PSS-based work. At CAUS, I do thank my collaborators, Professor Daria Baran, who you will hear tomorrow about her fantastic printed devices, Khalid Salama for lots of integration work, and his student Jose, Husam Al-Sharif, who are the people who give us MXene and who teach us about it, and a few other collaborators in France who we collaborate for electromyography studies. Well, thank you very much for your attention. It was a pleasure to give this talk.
Thank you, Sahika, for this talk. I think we have some time for questions now. So if you guys have any questions, please write them in the Q&A, and then we'll let you answer to Sahika live. So let's just start with the first question. This is Jamie Sanchez. I'm just going to allow you to just to start the mic. Just 1 second. So you can unmute yourself now. Can you hear Jamie?
I can read the question, maybe the first one at least, because he has two questions. One is the distance between reference electrode and the actual channel or the electrode is relevant when measuring. Yes, it is indeed relevant, so we need to care how we are placing them. Can you please explain again how is SNR getting better over time using printed electrodes? So over time, the skin is generating, you're sweating, and if you're not in a dry environment, that is helping the device to better interface the surface. Because remember, it's a dry electrode, and if you have any liquids on the surface, things are going to get better. So unless you go to a very dry environment, the skin is going to hydrate over time. I hope that answered the question.
All right, so let's just go to the next question. This is from Saleh Hamid. Can you see that question, Sahika?
I do, and I'm reading it, Saleh. Are you working on plant sensors? We are not, but we would love to, because plants are easier than humans. They are easier to deal with. They have, I think, more tolerance to toxic compounds. Obviously, you don't want to kill them while you're sensing signals, but I think they are a much easier platform to work with. And we would like to do that in the future. Thank you.
Thank you so much.
I think next one.
The next from Altine.
Go ahead, Abdullah.
So the question from Altine is, are there strategies or methods to reduce printing resolution?
Yes, very likely. Well, we do not have them, but I think probably next talk, Atif Shamim's talk, is going to answer that question. We were so far okay with the resolution that we have, but obviously once you want to do much smaller things and have higher spatial resolution, you need to have smaller than what we have.
Right. We have next question from Shaban Oruj. She's asking, can we use the impedance as a parameter for further research?
Impedance as a parameter for further research? I mean, I think if you're talking about the as a measure of an electrode's quality, yes, of course. The higher the impedance, the worse basically the signal to noise ratio will get. But we do also realize that for electrophysiology recordings, unless the impedance is not too high, it is still possible to get some good quality signals. And I also need to say, it is important to, the electrophysiological recordings change from person to person. So if you have bad signals from one person's skin, which may be very dry, just move to the next one. But yes, you should be using impedance as a parameter to evaluate the sensor performance.
Thank you, Sahika. It was.
You're welcome. Mohammed is asking, Abdullah, I'm continuing. Is peanut PSS toxic? No, it is not toxic, but you should not eat it still. On the skin, it's fine. The cells are fine. If you grow cells on top of it, we don't see any toxic effects. But remember also, there are some tricks to make PEDOT less problematic, let's say, for living tissues, like, for instance, making a film and keeping it in water for a while and doing some cleaning procedures that is following that up. I hope that answered the question. Is there any infrastructure possibility for collaborative work? If you're talking about at KAUST, definitely. If you see my last slide, for only these 3 projects, we are already working with 3 different groups at KAUST. And if anybody else wants to collaborate with KAUST, we are also open for collaborations.
Okay, thank you. So as a like if I want to go for a project, a collaborative project in collaboration with KAUST and Princess Noora University, can we go for it? Because I work in bioimpedance analysis. So
excellent, Shabana. You can contact us via email, and I'm sure you will get some answers about that.
Definitely. Thank you so much. Thank you.
Abdullah, shall I continue or are you going to read?
Yeah, go ahead. So next question is from Athil.
You print the electrode using the printer, right? That is right. Is the polymer applied using the printer? Yes, you basically use the printer to print the polymer. Can you clarify how many layers? Yes, of course. So I think if you put only 1 layer of PEDOT, you will, depending on the concentration of the PEDOT ink, you may have a very thin layer. So that makes you to put a few other layers of PEDOT on top of it without, drying out PEDOT too much, so that, those multiple layers are not separated from one another. Okay. But typically we are using, I think, around 2 to 4 layers of PEDOT, right, Abdullah? I guess so, 2 to 4 layers. Or was it wrong? Just correct me if I'm wrong.
No, that's correct. That's correct.
Okay,
that's correct.
All right. Alavi, for the biosensor technique that is used for blood glucose, that was for saliva glucose. We haven't done that with blood, but I think that can work similarly. You mentioned that the varying the voltage supplies would allow for measuring dopamine, uric acid. Then you showcase that you could use some sort of photovoltaic to supply the voltage, but how would you control the voltage if it is supplied that way? That's a fantastic question. And I think I hope Baran is going to talk about it tomorrow. Solar cell voltage may be affected by the light intensity that you have. And then you use some other circuit elements to modulate or to fix that voltage at a certain voltage that you want. That is how we can do that. Next one is in Urba. What would you consider as a necessary property in a potential substrate material for printed electronics? That's also a very good question. A necessary property, I think, for a potential substrate, of course, depends on the material that you want to print. If we talk about water-based inks, of course, what you want is a hydrophilic surface. Because if your first surface, if your substrate is a very hydrophobic one, the water drop will not want to spread. And if you can't spread the drop, then you can't form a film. So that will depend on really the application that you're aiming, but also the material that you want to print. Considering you said researchers are looking for a broader library, you're absolutely right. So it's not only about the substrate. I think what we are more looking at ink formulations. Like if I have, for instance, PEDOT PSS as is, certain formulations cannot be printed easily. You need to put in certain things in it, like MXene that I showed to you. The first time Abdullah got the MXene, he could not print it because MXene didn't have the printable properties, biological properties. That's why he had to add certain solvents or surfactants to make it such that the properties are okay to print. All right. Meshar is asking, does the electrical conductivity of the printed material matter? Does it have to be highly conductive? Well, if you're using it as an electrode, yes, it does matter. It has to have, so I would not say high conductivity for, all right, hold on. The electrical properties or electrochemical properties matter, but it's not always that you want a high conductive material. For instance, if you're going to print a transistor material, you want a semiconductor. That means you don't want a very conducting film, right? You want a semi-conducting film, but a film that can change its conductivity upon gate voltage modulation. If you want to print contacts, silver chloride electrode, the reference electrode, the counter electrode, then you want them to be very conducting. So it doesn't have to be highly conductive. Again, depends on the application. The other question was, do you cover strain and pressure sensors in the inkjet technique? We do not do that, but there are some groups who are making such sensors as well using inkjet printing. I think that's one of the nice applications where you can use printing. Again, probably, if I'm not mistaken, Professor Atif Shamim might be showing some applications about that.
Right. There are a few more questions in the chat, so just let's take a look at a couple. Carolina is asking, is it necessary to have electronic knowledge when you're doing research about biosensors?
Well, depends on which part of the project you're doing. If you want to do the whole project, yes, you do need to have the electronics knowledge. But for instance, if you're the one who is responsible from functionalizing the surfaces, then you need to know a lot of functionalizing the surfaces with biorecognition units. Then obviously you need to be an expert in biochemistry.